Hello, welcome to today's session on Spearman rank correlation coefficient. In our last session, we'd introduced the concept of correlation, and we'd spent some good time trying to explain the concept of correlation as used in statistics. And we had said that correlation seeks to actually determine the relationship or the level of association between two variables. And we say this kind of relationship between two variables can be easily be determined by using either the Pearson correlation coefficient or the Spearman rank correlation coefficient. And so in our last session, we discussed more of the Pearson correlation coefficient, and we mentioned that this coefficient is commonly used when there's a possibility, first of all, of a linear correlation existing between the two variables that you want to compute their correlations. And we also say that data in that scenario is assumed also to be normally distributed. And because of that normality assumption, the Pearson correlation coefficient is regarded as a parametric test statistic. And so, but we said the scenarios when we have violations of those conditions. And we said that in case now you are dealing with data that is not necessarily normally distributed, and when you draw a scatter plot again, you don't see a linear correlation existing between the two variables, then it means it's not fit for you to use the Pearson correlation coefficient to determine the correlations. And therefore, you resort now to this Spearman rank correlation coefficient. Like you can see, Spearman was just the name of the proponent. Now, rank is because this correlation coefficient is based on ranks. So the data must be put in ranks if it's not in ranks, or in other words, must be put in some ordered manner. Ordered means it can be reorganized in such a way that those variables are arranged from the smallest to highest separately, or from highest to smallest. That is what we call ranks, or ordering, or making it to be ordinal data. And so we say this is an alternative method to Pearson because this is non-parametric in nature. It is not having that restrictive assumption of the data having to be normally distributed. And so, and we are saying again, there's no need for linear correlation to exist and involves ranking. So we rank the data of each variable, and then we assess the difference between the ranks. So having emphasized that in this case now the data must be ordered, or the data must be in ranks, and by data here meaning that each of those two variables that we are interested in assessing the level of association, their data must be put in ranks. So the formula for computing the Spearman rank correlation coefficient is this. It is 1 minus this fraction, and this fraction is 6 times the sum of Rx minus Ry squared over n minus n squared minus 1. And so this can still be simplified. The Rx minus Ry can be written as di, can be represented as di. So di here is actually the same as Rx minus Ry, but it can also be Ry minus Rx. Remember, we are squaring, and so if we are squaring the differences, it doesn't matter whether you are talking of Rx minus Ry or Ry minus Rx, because you'll eventually get positive figures. And so what Rx and Ry here stands for is that Rx and Ry represent the rank of values of X and Y variables. So Rx is the rank of values for the variable X, and Ry is the rank of values of variable Y. And then N, I'm sure you can also see N. N in the formula now here represents the number of pairs of items in the sample. So you are given a sample size N, and this sample size N has to have at least the 2 pairs of variables that we want to compute the correlation. So you can have a formula with D in the absence of R's, just to make it more simpler. So we have said that there is a difference between each pair of rank measurements. Something important to note, whenever we are computing this correlation coefficient by Spearman, is that when ranking the values of the variables, each variable is ranked separately. So you rank that column of Y alone, then you rank also the column of X separately before you carry out now the corresponding differences between those values. So then we are saying again that ranking can be done either in ascending or descending order, but the same order must be used for both variables. Yes, you can decide to have that problem. You rank Y in ascending order, you rank X also in ascending order. And so if you have ranked Y in descending order, then X also must be ranked in descending order. You don't interchange. And that is very important for us to note whenever we are doing that. Maybe we look at this example. So where we are having now some data on finance, and this data is about 12 employees. They have been given the identities A, B, C, D up to M. So we have salary and house rent as the variables. And so if you are to use this data and compute the Spearman's rank correlation coefficient between the monthly salary and rent paid by the employee, you can see from the way the data is not ranked in any way. You have 45, 35, 24, 55. It's just mixed up. So there are no ranks. So if it was Pearson correlation coefficient, then it would have been easier for us to just go ahead and use the data the way it is. But because it's Spearman, we have to rank this data. And before you rank, remember we have said in these formulas, the formulas do not have salary and house rent. The formulas have the N, have the D, have the Rx. So you need, first of all, now to let's say, salary be represented by, let's say, variable X. And you can now represent house rent by code language Y. So that now, once you have now assigned them those particular variables, it is easier now for you now to get the rank of X and the rank of Y as separate columns. Besides this, the best way is to first of all put this table in vertical format as shown, so that now it is easier for you to create those other columns that we are mentioning. So that now you have something that this is now, these are the employees. So this is now the salary, we're calling X. This is the rent, the way it has been given. So the new columns you are adding so that we can now use the formula that we have stated above for Spearman rank correlation. I'm now having Rx, the rank of X. Now I'm ranking this column of X. And so I prefer using ascending, so that I begin from the smallest to the highest, so that when you look at this particular column, the smallest value is actually 20. So that's the one I'm assigning 1. Then the next one is actually 24, which I'm assigning 2. Then the next one will actually be 30, which is 3, all the way until I get to, I assign all of them from the smallest to the largest, which in this case appears to be 78. So that we will have a column of ranked values of variable X. We do the same to this variable y, which is representing the salary in 1,000 Kenya shillings. So we again, because you have a ranked column salary in ascending order, we also rank rent in ascending order. So we come here again, begin again from the smallest all the way to the highest, and you'll get, yes, here the smallest appears to be 10, and then you move on. The next one is 15, but 15 appears to be 3 values. 15 appears to be, no, the next one is number 2 is 12. So you have 10, that is what you have assigned 1. Then you have 12, which you have assigned 2. Then the next one is 15, but 15 appears to, we have 3 individuals are paying a rent of 15. Huh? There are 3 of them. So what happens here, if there are 3 holding the same position, so ideally, if they were not the same, we could be having they would be having the 3 occupying position 3, 4, and 5. So because they are 3 and they're tying, so what we do is that we get the average of the positions they would have otherwise held. That is position 3, 4, and 5. So we add 3 plus 4 plus 5, and the average of the 3 is 4. And so we assign each one of them now 4 as the average position for the 3, so that then the next position we shall be assigning will be position 6, because we have now position 4 is holding 3, is taking care of what we'll have had of 3, 4, and 5. So the next one we assign after this, which is 16, is now going to be assigned position 6. So that's how you handle ties. That's how you handle ties. You get the average of the positions, the number of ties hold. So if there are 3, so you're talking of the average of the 3 positions, which could have been position 3, 4, and 5. So once you have done the rankings for all of them, you now have the last column, which is supposed to be DI. I've called DI squared, or just call D squared for simplicity. So D squared, remember D is a difference. So 5 minus 6 is -1. Then you square it, you get 1. 6 minus 4 is 0. Squared is just 0. 2 minus 7 is -5. Squared is 25. 6.5 minus 10 is 3.5. Squared, you get 12.5. 8 minus 8 is 0. Squared, you get 0. So this is now the squared columns. So we are squaring the differences between the ranks. So we get absolute. Then at the end of it, all down here, we need to get the summation of this D squared. We need to get the summation. Remember, from our formula, we have said the formula says that we have 1 minus. So when you look at this formula, we need the D squared, the sum of that column. So when we sum that column, we get the whole of that particular term, which is our interest, because here we are talking of 12 pairs that form the sample size. So N, we have no problem. So when we sum from like our previous problem here, we get 135.5. So that is the only figure that we are interested in that table. And that is what we plug in the formula here, 135.5. So 6 times that, the sample size is 12 into 12 minus 1. So you're talking of 1 minus, of course, 6 times 135.5 over now 12 into this 144 and then 143. So you see you're getting a figure of 0.5262. That's a correlation value that is actually fit, is lying between -1 and 1, +1. And of course, this is an interpretation. This would mean there is a moderate positive association or positive correlation between the rent being paid in 1,000 shillings as well as the salary being earned by the employees based on this particular data. And so that is how we compute the Spearman correlation coefficient, slightly different from Pearson correlation coefficient.